kind of going over like the modes.
Yeah, I was gonna ask if you could go over like how to know when the node operates when you're solving.
Yeah, this is a very important question. Now, when you look at a waveguide, there's two things you need to consider, well, three. The dimensions of the guide for a rectangular waveguide with metal walls dictate the actual cutoff frequency for any mode. Second thing is what's filling the guide. If it's air, then the velocity in the unbound media is the velocity of light. But if it's not, you have to make allowances for that. And the third thing is the frequency of operation, or the frequency that's exciting the guide. You all with me on this, class? Now I'm going to do one thing. I'm going to address all your questions about the modes. Modes are just the allowable frequencies, you might think, that can actually propagate down a guide based on a cutoff frequency. When we have a rectangular guide, as such, we'll call that the x direction, and that the y direction. The width is, I forgot to get my waveguide. I may run up and get it during the quiz, just to show. I'm not sure, but I'll definitely make it a point to bring it. Now I'm assuming that this thing is, filling the guide is going to be some mu and some epsilon. Usually mu relative is going to be equal to 1. You all with me, class? When we have this thing actually looks like something that limits low frequencies. It is a high pass filter. You need a frequency, a minimal frequency in order for things to actually propagate. Now, when we talked about the TM mode, you all remember this? For the TM mode, we found that the actual field EZ is given as some E naught, and it's going to be times the sine of m pi over a times x, and times the sine of n pi over b times y. I forgot the y in there. And then it's times e to the minus j beta in the z direction times z. And Whitmore's book, he just calls this beta. I prefer beta z because it indicates the direction that beta is associated with. Beta, usually without a direction, is free space beta, but he uses beta unguided for them. And it's in the a z direction. Now, I didn't derive all the field components, but if you have this EZ, you can go ahead and get EX, EY, EZ, or HZ, and HZ 0. You can get HX and HY, and I'm just going to tell you how. If you go ahead and take the curl of this E here, you're going to get some partial terms, but you're going to get full terms too. And then for that, when you look at curl of H, that's going to be minus j omega mu, and it's times E as such. When you take the EZ component here, write the formula for curl, and expand this. I'll do this, not today, but we can do this then. You can get all the field components. And in Whitmore's book, for the TM mode or TE, it won't matter. The field, either HZ or EZ, dictates all the other field components. In this case, let me go through this. This is chapter 7. I just want to give you the page number because this is important stuff. So for TM modes, all the field components are given on page 390, and he starts with equation 7.42. And what he's going to do is just get the other components by doing curls. That's all he does. Now, I'm going to tell you some of this gets tedious if you do them yourself. But it's doable, and we can talk about it. I haven't done that in a while. I may go ahead and do it. He has all the field components. And then he even shows a plot of what the actual magnitude of, for instance, EZ looks like for the different modes on page 392. When you look at this for TE mode, and this is important, all right, the smallest or lowest operating frequency is going to be in the TM11 mode, which indicates m equals 1, n equals 1. Now the cutoff frequencies are given by an equation, and they're given by the same equation, TE versus TM modes. The cutoff equations for m, n are equal to 1 over 2 square root of mu epsilon times the square root of m over a squared plus n over b squared. Those are the cutoff frequencies. A lot of times in non-magnetic guides, you'll see these are cutoff frequencies, Fc of m comma n, given as simply c, because 1 over square root of mu naught epsilon naught is the velocity of light. Are you with me on this, class? What they'll do is put this divided by 2 square root of epsilon relative. Now, if it's air-filled, it's just c over 2. Everybody with me? Then you're going to have the square root of m over a squared plus n over b squared. And in fact, that'll give you the cutoff frequencies for any mode. The lowest TM mode is the TM11, all right? That means m is 1, n is 1, and that will give you that frequency. TM11 has to be higher than TE10. You all with me on this, class? Or TE01. Either one of those two are lower frequencies. So this really, I could put down all the field components, EX, EY, EZ. I can put down HX, AY, HZ, and do all the curls and just probably bore you to death on those things. But you can get them all, and they're stated explicitly in Whitmore's book. Are you with me, class? I would not ever ask you for HX or HY from this equation right here. I would specify if I was asking that. I'll show you some tricks and get it though later. Yeah.
So like in the homework that you gave us, it specifies that the guide operates at 20 gigahertz. So you compare.
That's the frequency of operation.
Okay.
And now the modes we're going to get to. How do you know what modes will be developed? All the frequencies that are above the lowest cutoff to that frequency.
Okay.
Any frequencies, any modes that have a higher cutoff will never be developed. Just follow us. I want to do the TE now. Now this is the TM mode. That's EZ0, right? And I'm not going to spend a whole lot of time, but you'll see this. So if we have this guide and we assume EZ equals 0, that is transverse electric mode, TE mode. How many understand that? Just let me know. Right? If E field in the Z direction is 0, it's TE, pardon me. If H field in the Z direction is 0, that's TM. All right? So for this one, we would assume that we have an H field in the Z direction. In Whitmore's book, I think he calls it HC, but I gotta be careful because sometimes he surprises me. This is a very simple book. He's not really throwing any high-level theory and stuff like this. If you get into some of the other books, even at the undergraduate level, they're very theoretically difficult or they're more complicated. So let's see. There's TM. All right, he does use H, so I'm going to do that. He does have an HZ equation. Yeah. All right, now I'm going to go through this kind of quick, but follow me. VZ is 0. We're going to assume HZ is in fact something that we need. All right, there is an HZ. I'm just going to tell you what it's going to have a form of. The way I get it is just like with the E field. Do you remember this field equation? Del squared of EZ plus omega squared of mu epsilon. EZ equals 0. Do you all remember that when I put it up there? I got that from the two curl equations, and I developed this making an assumption, right, that we're inside the guide, it's propagation, it's lossless. It came down to that equation. Then I used, you remember what I did to solve EZ? Anybody? There's one singular trick I did that's from the mathematics department, I call it. It is a, what, separation of variables. So we assume a solution, put them in there, and we figure it out. Y'all with me? If you wanted to, I might as well just do this real quick. If I take this equation right here, and you don't have to write this down, just watch. If I take curl of H, that's equal to gradient of divergence of H minus del squared of H. Now that's just a vector identity you're gonna have to accept. You with me on this, class? That's equal to, well, curl of H, here's curl of H, is equal to minus j omega mu, and then it's gonna be curl of E. If you let me just finish this, I can talk my way through it. You all follow me in the thoughts, right? Curl on both sides? Well, what's curl of E? I didn't put it down, but curl of E is what? I'm sorry, this is curl of, sorry, let me do this. No. Oh, no, that's fine. I can do it this way. I should put down curl of E. Let's do it this way. Curl of E is minus j omega mu times H, and then curl of H, I had this operator order thing, is equal to j omega epsilon times E. And the only thing I'm trying to do is, and I'm assuming sigma is 0, so it's losses. Can you all follow me on this, class? I'm sorry if I confuse you. So now, if I take another curl of this curl of H, which is there, I get this, and then for curl of E here, I'm going to substitute that, and I'll put it right below here. So I'm going to go ahead and get omega squared mu epsilon, and this is going to be times H. So that's this right here I'm substituting in, and that's going to be equal to, and if you give me your attention for 1 second, I won't fly, but listen, what is the divergence of H?
0.
Why? You're right.
Charge-free medium.
Not charge. It's no magnetic monopoles. Remember, divergence of B is rho V. Divergence of B is equal to 0 because rho M equals 0 always. There are no magnetic monopoles. Do y'all remember? I don't know if I taught you guys EMAG 1, but this is something you have to know. So that means this, by definition, is 0 always right there. If that's 0, I have this, right, down here. And now I can make my case. I can just say, well, this plus this has to be equal to 0. All right? Now that has H itself will have 3 components generally. We only care about the HZ component. Remember, EZ is 0. The reason we do is if we had an EZ component, we start messing with these curl equations, you're going to get all this stuff that you can't separate. But for this case, we can. Now we come over here. And now I show you the exact parallel, or the analogous field, or an analogous form of an equation with HZ. So you get del squared of HZ plus omega squared mu epsilon times HZ is equal to 0. It's identical to this form. Y'all follow me? That's the only thing I'm really trying to do. Take this form and use separation of variables. Now, I did this before. Let me do it over here and just kind of blow through it. I like this side of the board better. I think there's a light out there, isn't there? Talk to management about that. So now I go ahead and I say HZ is equal to some function just of X, just of Y, and just of Z. As before, you go ahead and plug it in there, right? Remember that del squared operator implies derivatives of HZ with respect to X squared, Y squared, and Z squared, right? Add it together. So I get, when I do this, I get the second derivative of HZ with respect to X squared, plus second derivative of HZ with respect to Y squared, plus second derivative of HZ with respect to Z squared, plus, and then omega squared, I'll call this beta unguided, which is omega times square root of mu epsilon, plus beta unguided squared. All right, and then it's going to be times hz equals 0. Y'all with me? I know I've done this before with EZ. Now you go ahead and make the substitution in there, and you see you get x double prime yz as before plus x times y double prime z plus, and now you're going to get x times y times z double prime plus beta unguided squared times x y z all equals 0. Do y'all follow me? I'm just doing the same thing I did before for EZ, correct? I won't ask you to prove this, by the way. These are things, higher level courses, maybe senior level graduate courses. They'll ask you to go through this whole derivation. They give you a piece of pencil, give you a pencil or a piece of paper, and just, you have to do it. You have to know how to do this like V equals I. You gotta know that. Okay, I get down to this point. Now I divide everything by x, y, and z, as before. If you just follow me on this, you don't have to write everything down, but you can follow me with what I'm going to get. Now I'm going to get this over x, right? Just the function of x. I'm going to get y, not y. It's going to be plus y double prime over y. These are just functions of x, just functions of y, just functions of z. And this becomes plus z double prime over z. And this becomes just plus beta unguided squared equals 0. I'm doing it one time like this. Agreed, everyone? I'm going to get to your point. Trust me. Get to this point. Each one of these things can only be a constant because that's just the function of x, right? Just the function of y, just the function of z. The only possibility that would allow this to happen for any values of x, y, and z is if each one of these terms is a constant. Well, beta unguided is already a constant because we operate at a single frequency. So that means now this becomes, as before, minus beta x squared. This becomes minus beta y squared. And this becomes minus beta z squared. And I'll do one of them and I'll show you the result. Y'all with me, class? Y'all remember doing this? At least vaguely, right? Because I kind of went through this in life. I think you said that these kind of proofs they don't exactly sit well with some students, but I understand that. I was sat where you were at one time in my life. And I have to force myself to focus and understand this stuff. It's not always easy to do that. You have to make a tremendous effort sometimes. When I get down to here, I'm going to use the x double prime one. So x double prime over functional form of x means is equal to some minus beta x squared. Here I'm going to take x double prime, and then I'm going to have plus beta x squared times x equals 0. Does everybody know what I've done from the first step to the step? I rearranged things to make it all equal to 0. This double prime is the second derivative of the functional form of x with respect to x squared. And this is going to be plus beta x squared times the functional form of x equals 0. That's the second order differential equation that's linear. Last time we talked about this, somebody said use an integrating factor. I don't remember who it was. Do y'all remember for the solution? We could use Laplace transforms too, but it would be a Laplace transform with a spatial, not temporal formulation. And you can go without. Either way, you're going to get solutions of x. And remember, this x is going to be multiplied by some y function times some z function to beat h of z. Do y'all follow me? Now, with that in mind, when I look at this x of x, and that's a linear differential equation, you can have solutions of the form, and that tilde just means these types of solutions. Either a sine of beta x times x, or it could be a cosine of beta x times x, or it could be e to the plus or minus j beta x times x. Do y'all follow me? Those are the allowable forms of solution that will solve this. Does everybody at least understand, appreciate the fact that's how you get it? Now, what about the last one? Is this allowed? Remember, that's the explanation. Yes or no? Go ahead. It's propagation, right? Some people will say, well, you can make the sign e to the j beta x minus e to the minus j beta x over 2j. Yes, you could fuss with it. Frankly, this by itself is a propagating wave. You know with me? So we get rid of that. This is no more. Now it gets interesting. Here we have either sine or a cosine for h of z. And this one is going to take a little thought. Remember, the boundary conditions were the things that prevented the cosine from being a functional form for ez. Do you all remember that? Remember, the sine was the only one that met the boundary conditions, right? So here's the origin of 0, 0. This right here is going to be a, 0. This is going to be 0, b. And this is going to be a, b. I'm just showing you the 4 points that bound the region. Now, when you're at these boundaries, we know that the tangent electric field, in this case, Ex at this boundary will be 0. You don't know about the H field boundary that wasn't talked about earlier. So you know that H tan 1 is H tan 2. Y'all remember that? The boundary condition class? H tan 1 equals H tan 2 is a very interesting thought. If you look at the derivative of H in this direction, if you had an Hx there, the derivative of the tangent component, I'll put tangent, with respect to the normal direction is 0. This is not something that you've seen before. You're going to have to appreciate this. If I take a look at this, and you look at, let me try to do it here. I'm showing you, what I'm trying to do is show you that the actual inner part of the waveguide, all right? If you were to plot the H field versus height on this thing, what you would say is this, that the H field would start at for all modes, but I'm going to just show you one. It would show a maximum, then it would become 0 right here. I'm trying to show you the magnitude of, say, I'll call it HZ, because that's, we have EZ equals it. Then down here, it's going to become a relative magnitude. And if you were to extend it, this waveform here would look like a cosine waveform plotted this way or this way. Can you understand that, class? The derivative of a cosine waveform, where it's a maximum, is 0. Do you all follow me on that? Now, what happens is the H field that is tangent to the boundary, the derivative of that with respect to the actual normal, or the direction that you would have to go in to go through the boundary, is 0 always. And there's more to this one. Whitworth's book kind of just, did anybody read this in Whitworth's book? He just kind of talks about it. Now, the way you get it is from the curl of H equation. I don't have time to go on that right now. He just states it, but that's the truth. Because of that, you know that the derivative of Hz with respect to the normal direction, which it can be x or y, we'll call it y direction, the lower bound, has to be 0. Well, what's the derivative of the sine? It would be beta x times cosine, right? A cosine, when x is 0, is 1. You don't meet that boundary condition necessarily. Do you all follow me? This is a tough one to think through. You're going to have to spend a little time. But the sine, but the cosine does. When you take a derivative of sine, you get cosine. You can't use the sine. Has to be cosine. And that means for this one, Hz is going to have it's going to be of the form of some constant. I'll call it H naught. It'll be cosine now of beta x times x. I'm going to go ahead and just tell you. It'll be the cosine in the y direction too. You all with me? You can look in the book. You'll have this. This is going to be cosine of beta y times y. and it'll have the same form of propagation. It'll be E to the either plus or minus J beta, and this is in the Z direction, times Z. And this, of course, is HZ. Now, in his book, he'll give you this equation, but for beta, he won't have beta Z, he'll just have beta unguided. Or, I mean, regular beta. And this is equation, oh, where is this? Yeah, equation 7.70 on page 396. Do you see this, guys? I'd write that down. And he has all the field equations. And I think in one of the problems in the book, he asks you to derive the field components. I'm not going to have time today to do it, but I'm going to tell you the only thing you're going to do is start with that HC, and you're going to do a curl of it, and you'll get the E field components, but I'll spend more time doing it later. I haven't done that in a while. In fact, I may find myself trying to do it quickly. Now, there's some things I'm going to tell you about this. Remember, for TM modes, this is the form, right? And I didn't do this, but if you look up here, the beta X and beta Y will be the same exact form as they were for the TM mode. All right, so the beta X and beta Y come from boundary conditions. Let me just do this, and let me write wow. I want to just showcase this. So for TM, let me do it this way. For TM modes, lowest is M equal 1, N equal 1, right? And for this, EZ is equal to some scalar E naught times sine of M pi over A times X sine of N pi over times Y over B. And then it's E to the minus J, and I'll call it beta Z times Z. That is for TM. For TE modes, the lowest possible mode is going to be M equal 1, N equals 0. This is the lowest possible mode, the lowest frequency of propagate. You might want to write down, that's the one that all rectangular waveguides are designed to allow to propagate. All the other ones will be prevented. So the waveguide's dimensions are limited by the allowable frequency you want to propagate. Let me tell you a few other things in a second. So this one will have some HZ equal to H naught cosine of M pi over A times X cosine of N pi over B times Y and times E to the minus J beta Z times Z. That will always be the case. The cutoff frequencies are given by this, and the lowest order cutoff frequency will be the TM or TE10 mode. Y'all with me? TM modes have to be, both M and N cannot be 0. The lowest value they can be is 1. Now, typically, here's how a guide works. This is addressing your question. When you have a waveguide, the horizontal dimension is A. Actually, the longest dimension of a rectangular waveguide put on the horizontal axis. You don't have to, but for analysis purposes, it'll make a little more sense to talk about it that way. This dimension, almost always, B, is going to be less than A over 2. Not always, but almost always. Now, here's why. Because if you look at the cutoff frequencies here, let's just talk about this. Now, let's assume that this air filled. Let me move over here. Really want to make it. An air-filled guide like that, and we want the cutoff frequencies. So FC10, and this is a TE10 mode, That frequency would be, if you look here, it's just C over 2. Everybody with me on this? So it's equal to C over 2, and then look, M is 0, so I have M over A squared square root, it's just 1 over A, right? That's the TE10 mode. I want you to take a look at this for a second. I cut off. What? Now think now. If that's the cutoff frequency, what is wavelength in terms of frequency if we're propagating in air or in a vacuum? It's what? C over F, right? Do you agree with this? Everybody? How many know that, please? Just let me know I'm talking to you. You understand, right? All right, so the cutoff wavelength for the 1O mode will be C over the cutoff frequency of the 1O mode. And that means the cutoff wavelength for the 1O mode is equal to C. Now look, I'm going to divide it by that. It's C divided by C, right, over 2A. Can you all follow me? Now just listen, right? What does that imply? Well, C's cancel, right? And what do I end up with?
Constant.
No, yeah, you get a constant, but it's 2A, right? Now just listen. If 2A is a wavelength, what is this? Exactly half a wavelength. At the cutoff frequency, I can look at a guide and I know the lowest frequency it'll pass. Just say that's a half wavelength. If that half wavelength, I know, I can figure out what the frequency of cutoff is. You all with me, class? Now, the next highest order mode, almost always, is going to be, and I'm addressing your question. So the highest or the lowest order mode is TE10. Where did I put that? Did I erase that? Yes, I did. So well, it's right here, TE10. The next mode is going to be TE20, almost always. Not always, but 99% of the time. You want to there's only very stupid, not stupid, very selective reasons for having a cutoff frequency not be 2.0 next. And that would be if you're trying to throw a ton of power down here, so the height of this should be higher for breakdown. Don't worry about that. Nobody does that in the real world. Well, they do it for pulse power applications, but, and maybe there's something else, but if they want pulse power, usually they're going to use cylindrical waveguides. They're not going to do it. You know, I could be wrong about that too. Just let me finish on this one. So for the cutoff frequency for this mode, 2.0, TE20, I'll call it TE20. Well, that cutoff frequency is what? Just think about it. If this is, think about it now. It's going to be exactly what? Twice this frequency. The wave, right? Isn't that right, class? Exactly twice. So it's just 2 times the cutoff frequency for the 1.0 mode, right? You don't follow me. Go ahead and just put it in here, right? Instead of a 1, I got a 2. I got a square. If the 2 comes out in front, the cutoff frequency is twice the 1.0 mode, right? Now, that's the first and the second mode, almost always. Usually, the next 2 modes that appear concurrently are the TE and TM11 mode, all right? Typically, well, I say that, but here's what you got to check. You got to see you got to take a look and see if the TE01 mode, and that would mean B is greater than, it's bigger than half, but it's larger than A over 2. I'm going to do it over here. I'm going to try to make sure you guys see it. And I'm doing my best here, and I want to make sure I address this, why certain things happen the way they do. So now we're going to take a look at a couple other things. Remember, I made this assumption. That's 99% true. All right. Let's take a look at the next logical frequency. FC, we've got the first frequency is right here. Second is here, almost always. I mean, I can't think of a case when that doesn't happen for regular. Now we're going to take a look at 2 things. Let's take a look at the O1 mode. Well, that would be C, right? Over 2, and I'm assuming it's airfield. Do you agree with that part? Now, the M is 0, and I have 1 over B. So I have 1 over B here, right? Now, if it was 1 over A, it would be the 1 ohm mode, right? The second mode was really what? It was twice the first mode, right? But because I made this provision that B is less than A over 2, right, we take a look at this mode. And it depends on the actual dimensions, but think about this. What happens if B is equal to A over 2? Then you get what? C over 2, then you got A over 2, right? That's C over A. Take a look. C over 2A first mode, C over A second mode, right? Y'all follow me? That's twice this mode, twice this frequency. Well, then all of a sudden this happens at the same time, doesn't it? So you get the O1 and the 2O mode appearing at the same time. Do y'all follow me? That is really bad for a lot of reasons. You don't want that. So what we always do is we make the provision that B, I mean, not always, but unless there's some really overwhelming, crazy reason, we assume B is less than A over 2, all right? So that means the next mode, likely next mode, would be the O1 mode, TE01, but you gotta check it. So it's probably gonna be the TE01 mode. And then at the same time, you gotta take a, what is that mode? It was what? I just put it here. This right here, right? Now what about the TE11 mode, or these are the same exact frequency, TM11 mode? What do they give rise to for a frequency? Well, that's going to be what? C over 2, right, for airflow, correct? And then it's going to be a square root of 1 over A squared plus 1 over B squared. You've got to take a look at that one. But just looking at it, you'll notice that C over 2B, right, forget the A, that's going to be at a frequency that's lower than this because you got to add 1 over A squared to it inside that. Y'all follow me? So the progression, usually TE10, TE20, and you got to check it though, TE01, and then TM-TE11, usually. Now, I hope I'm answering your questions. So I got to tell you one other thing too. All these different modes for a given excitation frequency propagate at different speeds. The 1O mode propagates at a faster speed than the 2O mode. And here's the problem. When you've got a waveguide and you're trying to get, say, communication information down a waveguide. So, do you know how you excite a waveguide anymore? Do you know how you actually power these things? Put a little antenna in there. We didn't cover antennas, so I can't effectively talk about it, but let me just show you what these things look like. And it really, really does help. Like, kind of visualize what's really going on here. You've got a resonant cavity. I mean, not a true resonant cavity is all closed up, but you have something that only works, or only certain modes or type of wave patterns develop when you're beyond a certain minimal frequency. The reason it happens is then when the wave's bouncing around in there, you get constructive interference and the thing will propagate. Otherwise, the thing won't propagate. So if you have a waveguide as such, and I'm trying to draw this so that you can see it. What they usually do, this is a rectangular guide, right? This is the Z direction way it's propagating. They cut a little hole here. And what they'll do is stick an antenna into the guide, a very short antenna. Now, that antenna's impedance, we haven't gotten to that. That will be such that over here you're going to have a source. The source has some source resistance, and you're going to have this kind of a deal. You're going to have to just accept this. You're going to have some V source. Well, this little bit of antenna has an impedance. That impedance is going to be matched to the characteristic impedance of the guide. So there are no reflections at that point. This is a little deep right now. So what is a logical question is, what is the impedance of the guide? Make sense? And we could do it, we could go, the way you calculate impedance for the guide is, you really take EX, or really, yeah, EX over HY or HY over EX in magnitude. You're gonna have to take my word on this. And it's a little beyond what we can do right here, right now. But when you look at the impedance of the guide, now this you write down. The impedance of the guide for TE modes is equal to the intrinsic impedance of the material filling the guide. And I'll just call it eta guide. And eta guide here is just equal to the square root of mu over epsilon. You're not going to get loss in materials, trust me. Any functional guide won't have anything of a high loss. It might have a very low loss. You all with me? It's about real. So this, if it was free space, would be 120 pi, if it was air, right? And it's going to be divided by K. Now remember that magic number K is equal to what? Square root of 1 minus, it's the cutoff frequency of the mode you're talking about, right? Divided by the actual operational frequency squared, right? And for the mode to work or be developed at FC, I mean, F has to be greater than the cutoff frequency, right? Usually we work in a 1.0 mode. So you work between either FC 1.0 or 2 times FC 1.0. That's the way it always is. So that's the value of K. That's the impedance, and if it was air-filled, this would just be 120 pi over K. Now, the TM mode, which nobody's going to use, with maybe very, very few exceptions, that I can't think of a good reason to talk about that from a thing. But the TM mode is going to have eta of the guide here, and it's going to be times K. Now let me talk to you about something. Remember, this is the impedance of the guide. One thing you'll notice is, as you get closer and closer to cutoff, you see how K becomes 0 here? As you get closer to cutoff, the impedance of the guide is becoming infinite. And at cutoff, no matter what you do, you can't excite the guide. You can't get anything in there. Now, guides are typically operated at about a minimum of 10% above the cutoff frequency, usually a little higher than that. So if, say the cutoff frequency for the 1.0 mode was 8 gigahertz, with me on this? And for a rectangular guide, the 2.0 mode would be 16 gigahertz, right? They're going to operate somewhere between 10 and 12 gigahertz. It'll be at towards the lower end of the allowable frequencies, but not at the middle, typically. Y'all with me? Now, there might be exceptions, but you've got to operate in that range. They don't want to operate too low because the closer you get to the cutoff frequency, remember, here's what's really going on in this guide, and I want to give you guys a mental picture. Just follow me on this one. Think about this with me. What's happening is this wave is ricocheting, right? All right. Now it's moving, if it's air-filled, at the speed of light. Bang, 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 right? But you can see the component of velocity in the direction of the guide is less than the speed of light. Can you all see that? Wasn't it better? This one? What happens if the thing is operating at cutoff? At cutoff, the wave's just banging up and down. There is no propagation. So you don't want to operate the waveguide too low. All right, follow me on this? If you operate too low a frequency, then your velocity of propagation suffers. Instead of being at C, you might be at C over 5 or something like that. There's other problems that happen too. As this thing's bouncing around, that increases the loss. Even though it's low, the closer you get to cutoff frequency for operating at the low end, the higher the losses down the guide. That's the reason you don't want to operate it too low. Now, as you get higher and higher, there's one other thing that happens that we don't talk about that much. The higher the frequency of operation, the more attenuation in the material of the guide. Do you know how there's an attenuation coefficient alpha, right? Alpha we could calculate is just equal to square root of j omega mu times, forget sigma, just j omega epsilon, but that epsilon would have an epsilon prime and epsilon double prime. Now, the higher the frequency of operation, the more dielectric losses we have, even though they're low. Do y'all follow me? So usually they're operating somewhere between maybe 30% above cutoff, all the way to almost, they can go all the way. I say that, I can think of examples where they do operate closer to the second cutoff frequency, but to the middle of the frequencies allowed, typically. If the range was 8 to 12 gigahertz, that's like X-band. They typically, I say 6 to 12, they'll operate somewhere between about 6, maybe 10 worst case, but they're not going to operate at 11, trust me. You're going to have to just take my word for that. And there's other reasons. Anyway, that's sort of what happens. Now, for a TM mode, or TE mode, that's the impedance, this is the impedance. Do you remember the phase velocity business? I talk about phase in group, right? So I might as well just talk about this. What's the phase velocity, regardless of the mode? If it was what? If it was air-filled, it'd start with C, right? And phase velocity is always what? It's faster than the speed of light in a guide, right? Because it has to do with this imaginary moving point. Right? So it'd be C divided by K, right? I'm trying to extend some of the things I think you're going to ask me anyway. So this is phase. What's the group velocity? Exactly. Group velocity is the one we care about. I mean, I'll ask you a question on phase, but group velocity tells me how fast energy moves, and that's just going to be C times K. Now, if it wasn't air-filled, then you need to replace that with the velocity of propagation in an unbounded media made up of that material. That's real important that you follow me on that. Out of curiosity, somebody should think this stuff. I think I heard somebody in the hall asking that when I was walking in. So here's my equation. Both of these have beta z, right? Well, what is beta z? Remember that. The way you get beta z is what? Beta z is equal to beta unguided, and I could put down times the square root of 1 minus the cutoff frequency of the mode you're talking about. Each mode has a different velocity over the frequency of operation squared. Or I could just say it's what? Beta unguided times K, correct? And that's K right there, correct, class? What is beta unguided, guys?
Omega over C.
Omega times square root of mu epsilon, and in air-filled, it's just omega over C, right, for air-filled. Now, I was getting there, and let me try one more time to do this without getting off track. So if you have, say I've got a waveguide, and I'm operating at a frequency beyond the 2.0 mode, the TE2.0 mode. That means the 1.0 mode's developed and the 2.0. Do y'all follow me on this? Now both of those two modes propagate with different velocities. So if I'm sending out communication information, some of the power is going to be exciting the 1.0, some of the power the 2.0. And you yourself know that now I've got information that should be in a coherent waveform, moving at different velocities. I don't even know how much is in either mode. And if I have an antenna over here I radiate it with, all of a sudden, instead of have a signal that might be AM or FM modulated, comes out of there, now it's garbled, it's junk. You have to have only one mode, so you have the velocity of propagation is only going to be of one. Go ahead.
So say I had to calculate like the base velocity for the 2.0 mode, would I take the K for the 2.0 mode?
Absolutely,
Okay.
absolutely, absolutely. That's it. All right. Now, some of the problems I asked, just ask you, what modes would be developed, right? What are the lowest order modes? That means the smallest frequencies. Well, cutoff is 1. Next one is 2.0. Might as well take a look at 0.1. Be sure that what that one is. then 1-1. Beyond that, you're asking, well, what were the last 8 modes or something? Nobody cares about that. They care about what are the lowest order modes. Really, the first TE10 and the first TE01, and then the 1-1 modes in both cases. That's it. I mean, I should say 2-0 mode too, but that's what you get. One other thing I'm going to tell you about this stuff with waveguides, because his book, he only does rectangular waveguides where he does Maxwell's equations. With waveguides, these are metal walled waveguides. The other type we didn't talk about, and I'll mention a little more information about, are cylindrical waveguides. Has anybody seen cylindrical waveguides? They're like a hollow coax. And that's used for stuff like microwave power. You know these microwave dishes that, you know what repeaters are? We basically have a microwave link between 2 points. Typically, I shouldn't say typically, I don't know that for a fact, but I'm going to guess a lot of them use cylindrical waveguides. One of the reasons is, with a cylindrical waveguide, the lowest operating frequency is the 1-1 mode. I can't do the math is Bessel function math, that's beyond you right now. But you can transmit right-hand circular polarized or left-hand circular polarized waveforms and maintain constant power. You know how? You haven't had it yet. I'm going to get into it when you get into radar and antennas, but you'll understand why that's important and what you got right-hand circular polarized, right? Didn't I talk about that?
Yeah.
All right, did I? I'm sure I did. What's the advantage of sending out a right-hand circular polarized? That's right. And when you're sending that out, that's exactly it. It allows you to discriminate much better what the targets are out there for radar applications or communication information. The power is always a constant. If there's no, peak trough, like with AC power and stuff like this, I mean, with a standard single phase power, it's going to be a constant, like 3-phase put up. That's going too far right now. Did you have other questions before I give you this? Now, how much time? I'm looking at about 20 minutes, isn't that right? Lunch quiz now, you got other questions? I'd be happy to do either.
Cool, 20 minutes.
Huh?
Cool, yeah, 20 minutes.
All right, why don't we do this? We got to separate. How about this row, since it's got a lot of people?